Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss vapor pressure of liquid solutions. I am continuing from the last class. Last class I have discussed solubility of a gas in a liquid and Henry's law, all things last class I have discussed. Some numericals also I have discussed. Now I am going to discuss vapor pressure of liquid solutions. Liquid solutions are formed when solvent is a liquid. This is an essential condition. Liquid solutions are formed when solvent is a liquid solvent. The solids can be a case. The solid can be a gas, a liquid, or a solid. Okay, solids can be a gas, a liquid, or a solid. Solutions of gases in liquids already I have discussed. In this case I will discuss the solution of liquids and solids in a liquid. Here I will discuss solution of liquids in a liquid. First I will discuss liquid in a liquid. Later on I will discuss solid in a liquid. Liquid in a liquid. Such solutions may contain one or more volatile components. This solid may be volatile or non-volatile. Okay, but here we will discuss volatile solid. Okay, then in this solution, in the liquid solution, in such solution may contain one or more volatile components. Generally, the liquid solvent is volatile. Volatile means it will vaporize fast. The solid may or may not be volatile, but solvent must be volatile. And this also here I will discuss properties of only binary solution, two component binary. That is the solutions containing two components, namely the solutions of a liquids in liquids. Now I will discuss liquids in liquids, but it may be solid in liquid also. But now liquid in liquid I am going to discuss vapor pressure of liquid solutions. Now we can consider a binary solution of two volatile liquids, and this how will you denote? Then this can be denoted, these two components can be denoted as 1 and 2. When taken in a closed vessel, both the components would evaporate. Here you are considering binary solution of two volatile, both are volatile liquids. Then one you can consider as a one component you can consider as a 1, other as a 2. When taken in a closed vessel, both the components would evaporate and eventually an equilibrium would be established between vapor phase and the liquid phase, because both are volatile. Then in vapor phase also both will be there, in liquid phase also both will be there. This is very, very important. In vapor phase also both components will be present because both are volatile, and liquid phase also both will be present. Then here let the total vapor pressure, just to consider total vapor pressure at this stage. Suppose it is the P total, a small p, and total you can write TOTL, total vapor pressure. Okay, then vapor pressure at this stage, that is the P total, and P1 and P2, suppose it is the partial pressure. P1 is the small p1 and a small p2. One means one component, two means another component. And P1 and P2 means that it is a partial pressure, partial vapor pressure of two components. And P total means total vapor pressure after adding P1 plus P2, just to suppose. Okay, and these partial pressures are related to the mole fraction. Already last class I discussed that partial pressure and mole fractions are related to each other. Then mole fractions for first component you can consider as a x1, and for the second component x2. Okay, then x1 and x2 of two components, 1 and 2. Okay, this x1 and x2 are mole fractions of the two components, first and second. The French chemist Francois Martin-Raoult, it is the name of scientist from the France. Okay, again I am telling the name, Francois Martin-Raoult. It is popularly known by the name Raoult's. In 1886 he has given some law. French chemist Francois Martin-Raoult in 1886 gave the quantitative relationship, not qualitative, quantitative relationship between partial pressure and mole fraction. The relationship is known as Raoult's law. This relationship means partial pressure and relation between partial pressure and mole fraction is called Raoult's law. And what is a statement of Raoult's law? Then this it's a statement I am telling you, that for a solution of volatile liquids, the partial pressure of each component in the solution is directly proportional to its mole fraction. Okay, means directly you can tell partial pressure is related to directly proportional to mole fraction. Means P1 is, mathematically you can tell P1 is directly proportional to x1, and P2 is also same way proportional to x2. Okay, then here first you see, when P1 is directly proportional, P1 is directly proportional to x1 means mole fraction. Then now just you convert this proportionality sign into equality. Then one constant is required. You have to multiply by one constant. Then that you consider as a P1 subscript 0, you can write upside. P1 upside write a small 0, subscript 0. Then this P1 0 is actually constant. where this P10 is the vapor pressure. You can tell vapor pressure of pure component. Its value will be fixed only. Always vapor pressure of pure component at you can say this thing at this pressure, you can say pressure and temperature will be means constant. P10 that is called a standard that is for vapor pressure of pure component, pure, nothing is mixed. That is why it is called a standard. 0 means always a standard. P10 or P10 you can say, that is the vapor pressure of pure component 1, because we are considering only one component now. That's why we are using 1 for component 1. And temperature is constant, same temperature. Similarly, for second component, same way you can write. P2 is equal to P2 is directly proportional to X2. This is the mathematical. But now again you convert it into the equality. Then P2 equal to P2 naught X2. Means now P2 naught represent the vapor pressure of pure component 2. Both pure you have mixed. Pure 1 component is also pure, and second component is also pure. Just you have mixed. Then it became solution. Okay. Then this two equation I told you, both are same. P1 is directly proportional to X2 and P2 is also directly proportional to P1 is directly proportional to X1, correct? And P2 is also proportional to X2. Later on you have converted into equality. You have introduced P1 naught and P2 naught. Okay. According to Dalton's law of partial pressure, the total pressure P total, you can write P total over the solution phase in the container will be the sum of the partial pressure of components of the solution, means P1 plus P2. In a vapor phase, in solution, in container you have taken the solution. Then in vapor phase, just P1 plus P2, that is the total pressure. Means P total is equal to P1 plus P2. Okay. This is over the solution phase. Now this you are knowing P total is equal to P1 plus P2. Then now you put the value of P1. Actually you want to correlate with mole fraction. Okay. Then now P1, value of P1 you put here. Then you know P1 is equal to P1 naught into X1. That you know. In the beginning I told you, you converted into equality. Proportionality sign you have converted into equality for the component 1. Then P1 is equal to P1 naught into X1. Then this value you put here in P total. P1 plus P2 is there. Then P1 value you put it. Then what you will get? You will P total will be X1 P1 naught. X1 P1 naught. And P2 also value you put. P2 value also you put. Then P2 is equal to X2 P2 naught. X2 P2 naught. Here X1 X2 is the mole fraction of component 1 and component 2. Then now again you have to this X1 value. X1 is the mole fraction. Then now if you are knowing you can say x1 if you are knowing, means either you can say for solute or solvent. Suppose x1 is the solute, then solute mole fraction you are knowing. Then what will be the solvent mole fraction? Solute mole fraction you are knowing. Then what will be the solvent mole fraction? Then I told you, remember that mole fraction of solute plus solvent is equal to 1. Then if you are knowing any one, then you can know other. Suppose now x1 value are knowing, then x2 is equal to what? 1 minus x1. x2 will be 1 minus x1, that is equal to x2. Correct? Then here in the place of x1 you write this value, x2 value, right? Because already in second term already x2 is there. This x1 also you want to know in terms of x2. In terms of x2, then 1 minus x1 is equal to x2. Then now both became in the same term, x2. This side also 1 minus x1. 1 minus x1 is equal to x2. Correct? Then now both are in the same. Both are x2. Correct? That is, now we are talking about the solvent. Other component, second component is 2. Then now it became in the place of x1 you have written 1 minus x2. In the place you wanted to know this, you want to bring both in the same term. Then x1 value will be what? X1 value, suppose you want x1 value, then x1 is equal to 1 minus x2. Correct? Then 1 minus x2 you write in the place of x1, and in bracket you write 1 minus x2, that is equal to x1 value now you are writing, and after that 1 minus x2 in bracket you are written, and P1 not was there, that will carry down, plus x2 P2 not, x2 into P2 not, second term you continue as it is, x2 into P2 not. Then now you got in both term you got x2, 1 minus x2 into P1 not 0, in P1 0 or P1 not you can say, plus x2 into P2 not. Then now just you can say this x2 is in both term, then take the common 1 minus x2 that is in bracket, and outside P1 not you have written, other term x2 P2 is there, then you just should take the x2 common. Then what you will find? Then you will find these things. P1 not is only one term, hence it will be P1 not plus, now x2 you take common, then inside you will get P1 not, P2 not minus P1 not. Okay, outside x2 is common. Correct? Means P total is equal to P1 not plus in bracket you can write P2 not minus P1 not, and you have taken x2 common, it is out. Then P total is equal to, now you are knowing that P1 not means 0, P1 0 plus in bracket P2 0 minus P1 0, that is in bracket outside x2. Then here what conclusion you will draw from this expression? This is the expression you derived, P total expression. Then here what conclusion you will draw from this? Then conclusions can be drawn from this equation. What? Then first conclusion, that total vapor pressure over the solution can be related to the mole fraction of any one component, because now both are in x2 term. Then first conclusion you will draw that total vapor pressure over the solution is there, above the solution surface vapor is there. Then total vapor pressure over the solution can be related in the mole fraction of any component. Correct? Here you have related with x2. Now second conclusion, three conclusion we can draw. The second is that total vapor pressure over the solution varies linearly with the mole fraction of component 2. Correct? Component 2. It depends upon component 2. Okay. This is the second conclusion, that total vapor pressure over the solution varies linearly with the mole fraction of component 2. It depends upon component 2 also. Okay. Then actually diagram I will try to send it. It is very easy. By seeing the diagram you can understand. Diagram, what is this now? That x1, one side, a starting point, x-axis, you start with x is equal to 1. X is equal to 1. x1 is equal to 1. x1 is equal to 1, and slowly that mole fraction of x1 will decrease. Okay. Then when mole fraction of actually it is this plot between vapor pressure versus mole fraction. Vapor pressure versus mole fraction. Then simply very simple concept is there. If mole fraction is more, means number of moles are more. Number of moles either for this thing, solute or solvent, whatever be. If mole fraction is more, then it will create more vapor pressure. More the mole fraction, then vapor pressure will be more, as per law. Then here this concept you have to use. If mole fraction is 1 is equal to 1, x1 is equal to 1, then in the beginning pressure will be more, means high, and as the mole fraction will decrease, then vapor pressure will decrease. Then x-axis vapor pressure, x-axis is this thing, I am talking horizontal, that is the mole fraction, and upside vertical is vapor pressure. Then you will find a straight line that from high, when mole fraction was 1, x1 was equal to 1, that time pressure was more, vapor pressure was more, and as the mole fraction will begin to decrease, then slowly suppose it is decreasing, then vapor pressure will also decrease. And when mole fraction of 1, x1 I am talking about, x1 will become a 0, then vapor pressure will become 0, nothing, means down, it will touch to the, you can say, x-axis. Okay, horizontal, that side there it will touch to x-axis, down it will come. Then in plot it will look like a triangle. Right angle triangle it will look like. Okay. Then like that way, if means you consider x1 is equal to 1 at the one end, and in the last end x1 slowly and slowly decreased and became 0. x1 is equal to 0, x1 is equal to 1, and first end and second end it became x1 is equal to 0. Then vapor pressure slowly and slowly decreased and it touched the x-axis at second corner where you have written x1 is equal to 0. Same way for x2, actually only in one plot you can two you can say a diagram you can make. Okay, only in one distance, one place only you can draw two plots. Okay, then now you have seen one end x1 is equal to 1 and other end x1 is equal to 0, means mole fraction from 1 highest to s came to the lowest, means 0. Now you think that reverse case for x2, when x1 is equal to 1, then in the mixture it means x2 was 0, correct? Two component is there, then x1 is equal to 1, it means x2 is equal to 0 because total should be 1. Total should be 1. Mole fraction of x1 plus mole fraction of x2 is equal to 1. Then x1 is equal to 1, then obviously x2 will be 0. Then one end, first end, only there you can write below the x1 is equal to 1, below you can write x2 is equal to 0. Then now again when x2 is equal to 0, then vapor pressure for x2 is equal to lowest, means 0, down completely. On the same scale where you consider for the x1 that high pressure was there, P1 was there, P1 was there. Now same you can say on the same vertical line where you have written that is the maximum, means P1, that maximum that become maximum is for always for pure. Maximum vapor pressure will be always for pure component. Always remember that for pure component will have maximum vapor pressure highest. Okay, for any liquid it should be pure, that is called pure solvent or pure component. Always it will be highest. Then that in the x1 case you have seen from it started from high, that is actually P1 is 0 because it was the pure. Then its vapor pressure was highest and P1 it started with P1 is 0 and slowly decreased and finally x1 became x1 is equal to 0. Vapor pressure became less. Okay, then this is a one line, a straight line you got, and you got just like a right angle triangle. Okay, and now when you will consider when x is equal to 1, then x2 will be 0. Only there down you can write where x1 is equal to 1 you have written, down you can write x2 is equal to 0. Now when vapor pressure for x2 second component is 0, this mole fraction is 0. For the second component mole fraction is 0. It means vapor pressure will be 0. Then you can this plot you can just like what you can tell, just for understanding purpose, because only in one diagram you are showing two plots. Then you can consider that plot is made only in a square way. In a square, just 4 lines you can within that, just like only in one page you have made both. Okay, graph sheet is there. Now suppose only in one graph sheet 2 plot you are making. Then now that one boundary you can draw. If you will draw, it will look like a square. Okay, just like a square. Every side line you can make just in a within. Suppose a small graph sheet is there. A small graph sheet is there, or complete one sheet also can consider. Every sides are equal. Every sides are equal. Like that way you can consider. Then now when x2 is equal to 0, then opposite of first side means third, that is also vertical. 2 vertical and 2 this will be there. Though 2 verticals are there and 2 horizontals are there. One horizontal means horizontal just opposite to horizontal down. X-axis just opposite above up, and left side no vertical line is there. Then right side vertical line opposite of first vertical line opposite. Okay, that side now you can consider that is also vapor pressure. That line also tells about the vapor pressure. Okay, it is also perpendicular just like first one. Then now this x2 is equal to 0. Then vapor pressure you check on the just parallel to the first perpendicular line was there, y-axis. Then opposite to y-axis, that again parallel line. Okay, perpendicular. Then that side if you will see, when x2 is equal to 0, mole fraction is 0 for x2, then vapor pressure will be 0 because mole fraction is not there. Then pressure will be 0. And again you think that now x2 is increasing, mole fraction of x2 is increasing. Then what you will think, now vapor pressure will just start increasing, begin to increase. As the x2 mole fraction will increase, then vapor pressure will increase, and it will go, you can say, some more than first one vapor pressure. P1 0 was there, then now it will go, you will see that its vapor pressure is more than first one. That you can consider as a P2 0 because it is also pure. Second component is also pure. Then but only difference is that both component is pure, but one component vapor pressure is less than other. Okay, then here P1 0 was component 1 was having that liquid was having less vapor pressure. Now other component, second component has more vapor pressure. That's why in graph diagram it is showing more. It should show more, and it will also look like a rectangle. Right hand angle you can say 90 degree it will make. Then you will find that two triangle it is forming, one for x1, and now slowly x2 became equal to 1. x2 is equal to 1 second, and x2 became 1. That's why when it became 1, that's why pressure was high, because mole fraction is maximum, then vapor pressure will be maximum. Then now you got 2 vapor pressure. For the component 1 vapor pressure P1 0, and for the second you got P2 0, but P2 0 is higher than P1 0. Correct? Then now what is the total vapor pressure? Then total vapor pressure is equal to P1 plus P2. Then if P1 0 and P2 0, if you will can say these 2 point, these 2 points P1 0 and P2 0, both you join, then that it will go from P1 is less and P2 is more. P1 0 is less, P2 0 is more. Then if you will join both point, then one line you can draw. Then one will be down, other will be up. Then that is called P total. P total is equal to P1 plus P2. Total vapor pressure. That line will tell about the total vapor pressure. And first triangle, that time first triangle when you were joining, when x1 is equal to 1, that time you form a triangle. Then this point also if you joined P1 0, slowly and slowly, means mole fraction from x is equal to 1 became x is equal to 0. That point and P1 0 point, both you join, then that will be called P1. Same way that when is x2 is equal to 0, means starting, and when x2 is equal to 0 starting point, and it became x1 is equal to 1 maximum, then here for the second triangle I am talking about, x2 is equal to 0, mole fraction is 0. Then when mole fraction became x2 is equal to 1, then pressure was high. Then now this from the starting and P2 not P2 0, if we will join, then it is called, that line will be called P2. Then one angle diagonal means you can say H, hypotenuse, that is the P1. Other triangle hypotenuse is called P2. And both when you have joined P1 0 and P2 0 have joined, again it is forming one triangle only. Then here hypotenuse is called P1 plus P2, that is the P total. Vapor pressure total above the solution surface, that pressure it will tell. I will try to send the diagram. Okay. Then third I am talking about conclusion. First conclusion I told you that total vapor pressure over the solution can be related to the mole fraction of any one component. Second, total vapor pressure over the solution varies linearly with mole fraction of component 2. And third conclusions, depending on the vapor pressure of the pure component 1 and 2, total vapor pressure over the solution decreases or increases with the increase of the mole fraction of component 1. Okay, already by the diagram I already discussed that depending on the vapor pressure of pure component 1 and 2, total vapor pressure over the solution decreases or increases with the increase of the mole fraction of component 1. Okay, because component we have started with x1 is equal to 1 and slowly decreased and it became x1 is equal to 0 at the end. Okay, and this three conclusion I have discussed you, and diagram also I have discussed. Here already I have told you that P total is equal to P1 0 plus this thing P2 0. P total is equal to P1 plus P2. Okay, means P1 0 plus P2 0, that is the total maximum value. And again you have to assume that component 1 is less volatile. That's why its value is coming less. Less volatile means its vapor will be less. Volatile means it will convert to the vapor. Liquid will convert to the vapor, but it is less volatile. First component you consider as a less volatile than other, second one. Then here you have to assume component 1 is the less volatile than component 2. Component 2, it means what? You can write P10. 1 is less than P10 is less than P20. P10 is less than P20. The composition of vapor pressure. The composition of vapor pressure in equilibrium with solution, because there will be equilibrium. Vapor and liquid, there will be equilibrium. The composition of vapor phase. The composition of a vapor phase in equilibrium with the solution is determined by the partial pressure of the component. Partial pressure of the component. By the knowledge of partial pressure of the component, we can know the composition of vapor phase in equilibrium with solution. If suppose U1 and U2 are the mole fraction, suppose U1 and U2 are the mole fraction of components 1 and 2 respectively in the vapor phase, then using Dalton's law of partial pressure, here this things one thing you note down, that in solution also mole fraction is there, because both molecules are both components are present in liquid form, and both components vapors are present in vapor phase above the you can say surface of solution. Then two phases are present, component 1 and component 2. Both vapor phase, both are present in vapor phase also, and both are present in liquid phase also. Okay, this is very, very important here to understand. In vapor phase, how much you can say component 1 vapor is there, how much component 2 vapor is there. Okay, that is the composition. And in liquid also both are there, component 1, component 2, but they are in a liquid. Then here either you consider U1 and U2 or Y1 and Y2, no problem. If suppose Y1 and Y2 are the mole fraction of the component 1 and 2 in the vapor phase, means above solution surface, above the solution surface, then using Dalton's law of partial pressure, same way you can write that P1 is equal to Y1 into P total. Okay, means above solution partial pressure of the vapor. That is same way you are writing that that is P1 is equal to Y1 into, you can say, total pressure, P total. P1 is equal to Y1 into total pressure, P total. P1 is equal to Y1 into P total. And same way P2 is equal to vapor pressure of second component is equal to Y2 into total pressure, P total. Same concept. Then here P1 and P2 both you are knowing. For component vapor pressure in vapor phase, that is equal to Y1 into P total, and P2 is equal to Y2 into P total. Here Y1 Y2 is the mole fraction in vapor phase, mole fraction of component and component 2 in vapor phase. Then in a general, you can write in a general way, you can write that you can write that P1 is equal to Y1 into P total. Already I have written that in general way you can tell P1 is equal to Y1 into P total. Okay, means what is the this thing mole fraction of any component that you can write into total pressure, because the upside you have made, that is the total pressure. Here above the solution, in that way if you want to know vapor pressure of component 1, component 2, then that time total pressure you have to consider, total pressure. Okay, this is important things here. One numerical I am discussing related to this, and this numericals, this new type of numericals can be asked in examination, in competitive examination also, in general way also. Okay, then question is question I will read, you have to understand it. It is a long question. Question is long, but it is full of concept. Only by one question you will get the concept and you can solve many question. Okay, then try to understand the question. I am reading question, then I will solve the question. Okay, then I am reading the question. Vapor pressure of chloroform CHCl3, this is the formula for chloroform, and dichloromethane, that is the CH2Cl2 dichloromethane. In methane 4 valence is there, you know, then 2 hydrogen is there and 2 chlorine is there, and CH2Cl2, and in the chloroform 1 hydrogen is there and 3 chlorine is there. That is the only difference. Here 3 chlorine and 1 hydrogen in chloroform, and in dichloromethane both 2, hydrogen is 2, chlorine is 2. Then vapor pressure of chloroform and dichloromethane at 298 Kelvin are 200 mmHg and 415 mmHg. That is the vapor pressure of both they have given, for both, for chloroform also and for dichloromethane also. Vapor pressure they have given and at a temperature 298 Kelvin. Now you have to calculate. First, calculate the vapor pressure of the solution prepared by mixing 25.5 gram of chloroform and 40 gram of this dichloromethane. One chloroform we have taken 25.5 gram and this dichloromethane we have taken 40 gram at the same temperature, means 298. Then second things what you have to calculate, mole fraction of each component in vapor phase. In vapor phase, what I discussed, that thing just now I discussed that. Then two things you have to calculate. First, calculate the vapor pressure of solution prepared by mixing 25.5 gram of chloroform and 40 gram of CH2Cl2, means dichloromethane at 298 Kelvin. And second, mole fraction of each component in vapor phase. Correct? Then here solution I am telling you this explanation. Here how will you solve? Then first of all, whenever you are solving the numericals, then you convert it, they have given in gram, mass of chloroform and mass of dichloromethane in gram they have given. Then first you should know that what are the number of moles of chloroform and dichloromethane. That you should know. That is the first thing. You calculate the number of moles of both. Then how will you calculate the these things? Mole, already I have discussed. Mole is equal to mass divided by molecular mass. Given mass divided by molecular mass. Then easily you can calculate, because now you know how to calculate the molecular mass. Then for chloroform, CH3, all you are knowing. For carbon atomic mass is 12, for hydrogen 1, and chlorine is 35.5. Then here 3 chlorine is there. Add all, means 12 into 1 plus only one hydrogen is there. Only one hydrogen is there. Then 12 into 1 plus 1 into 1 plus 35.5 into 3, because 3 chlorines are there. If you will add, it will come 119.5 gram. 119.5 gram means this gram is equal to 1 mole. And now you know how will calculate chloroform. Then 25.5 gram they have given. Then 25.5 divided by molecular mass 119.5. Then you will get, after solving, you will get that will be 0.213 mole. 0.213 mole. Similarly, CH2Cl2 mole also you can calculate. Moles of CH2Cl2 also you can calculate. Then here again you have to calculate the molecular mass. Then for CH2Cl2, now only 2 chlorine is there and 2 hydrogen. Easily you can calculate 12 into 1 plus 1 into 2, because 2 hydrogen is there, plus 35.5 into 2. If you will solve it, it will come 85 gram. 85 gram means 85 gram is equal to 1 mole. Then now easily 40 gram they have given, dichloromethane 40 gram. Then 40 divided by 85, you will get, after solving, you will get 0.47 mole. MOL, don't write MOLE. Okay, IUPAC, MOL only, MOL, mole, according to IUPAC. Not write MOLE, MOL, mole. And now you are calculating, now you are knowing calculated moles. Then moles of dichloromethane you have calculated, moles of chloroform also you have calculated. First work, important work you have done. Then now total number of moles, how much? Then add both 0.47 plus 0.213, both you add, you will get 0.683, means 0.683 moles, total moles. Why you have calculated moles here? Think. Actually always you should convert it into mole. First step, that is every time you will require mole only, not molecule. Mole only every time. That's why first step you convert into the mole. Then now why you have calculated mole? Then now you know that vapor pressure and mole are related. Vapor pressure and mole are related. That's why you have calculated mole. Then now here total number of moles you have calculated. Then now mole fraction now easily you can calculate. Mole fraction easily you can calculate. Then mole fraction of anyone first to calculate. As for example, dichloromethane you are calculating mole fraction. Then very easily you can calculate that. Now you are knowing total also and dichloro mole also you are knowing. Then dichloromethane mass is 0.47 mole. Mole is 0.47 and total is 0.683 mole. 0.683. Then after solving you will get 0.688. That is that you got the mole fraction of dichloromethane. Same way you will calculate. Actually this formula wise you have to not calculate. One you have calculated this things, dichloromethane, one you have calculated. Second, you need not require to calculate in this way. That is the keeping weight of chloroform and total, not required. Now one you are knowing, dichloromethane you are knowing, x1 you are knowing. Then x2, 1 minus x1. From the 1 you deduct this value. From 1 minus x1, that is x2. Hence from this 1 you deduct the value, that is the 0.688, that is the mole fraction of dichloromethane. That value deduct from 1, then you will get chloroform mole fraction. You will get 1 minus 0.688, you will get 0.312. That is the this mole fraction of chloroform. Then now mole fraction you are knowing. Then you know that mole fraction has relation with vapor pressure. Correct? Then now you have to calculate. What was you have to calculate? Calculate the vapor pressure of the solution. First thing, you have to calculate the vapor pressure of solution. Okay. Then you know that total vapor pressure, you have to calculate two things. First, calculate the vapor pressure of the solution prepared by mixing these two. And second things, mole fraction of each component in vapor phase. Now you have calculated this mole fraction, that is in solution. In solution you have calculated mole fraction. That you have to calculate separately for in vapor phase. Then now here just you know that total vapor pressure formula already I have discussed. Total pressure, vapor pressure is equal to P10 plus in the bracket P20 minus P10 outside x2. Okay. Then here you have to put the value, because now vapor pressure value already given in the question, 200 mm and 415 mm Hg respectively. Okay, both values are given. P1 value is given, P10 value is given, and P20 value is given. Then you put the value, P1 value also, and P10 value, and P20 value. Means a standard value for pure component is given in question. Then if you put all this value, means a 200 plus in bracket 415 minus 200 outside mole fraction x2, okay, x2 mole fraction of here x2, here it will be 0.688, x2 is equal to 0.688, that value we keep here. Then it became 200 plus in bracket 415 minus 200 in bracket outside 0.688. After that solve it. Then you will get 347.9 mm Hg. This is the total pressure, total vapor pressure of solution after mixing this thing, chloroform and dichloromethane. This is the total vapor pressure. Correct? Now, second thing calculation, that is the second mole fraction of each component in vapor phase. Each component mole fraction you have to calculate in vapor phase. This you have calculated mole fraction for solution in liquid way mixture. But now in vapor also both are there, component and component 2. So for that, there what is the mole fraction of component 1 and component 2? Because they are not in solution, their component mole fractions are different, and in vapor phase mole fractions are different. Then here how will you calculate? Then now formula already I have told you that P1 is equal to Y1. P1 is equal to Y1 into total pressure, total vapor pressure. And total vapor pressure you are knowing, correct? Y1 you have to calculate. Y1 you have to calculate, and total pressure you are knowing. And P1 is equal to, I told you na, P1 is equal to Y1 into total pressure. Total pressure. Here total pressure you are knowing. Y1 you are not knowing, and P1 you are knowing. P1 you are knowing, and this thing one letter. P1 you want to calculate mole fraction of each. Okay, the same formula it will use. P1 is equal to Y1 into total pressure. Then here you first calculate, you can say vapor pressure of chloroform. Then vapor pressure of chloroform, how will you calculate? Then now here these things, total pressure you are knowing, and this in question they have given component and component 2, component 1 and component 2 vapor pressure they have, it is given. Then for chloroform, first to calculate, then it is a 200 mm. 2 times you are using this value. Then 200 mm Hg into total this 200 mm Hg pressure is given. Then 0.312, that is the this things mole fraction for chloroform you have calculated 0.312, correct? Mole fraction of this chloroform is 0.312. Then this 0.312 into 200, you will get vapor pressure of chloroform. Means after multiplying you will get 62.4 mm Hg. That is the vapor pressure of chloroform. okay, in vapor phase. And same way you will calculate for CH2Cl2, dichloromethane. Then here 415 is they have given, 415 they have given, that is the vapor pressure, okay. Then now you will get for dichloromethane, what is the mole fraction? You have calculated already, that is the 0.688 mole fraction, 0.688, okay, into 415 they have given in question. Then after multiplying you will get 285.5 mmHg. Then you got the now vapor pressure. You got the vapor pressure for both component 1 and component 2. Here important things I am telling you. Here when you are knowing separately for component and component 2 in vapor phase, then that time whatever they have given for pure component, here chloroform and dichloromethane, there they have given the pressure. Then here for the total pressure, in the place of that you can write what is given pressure as for example 200 and 415. In the place of that you have to write, okay. Then mole fraction already have calculated, and this pressure is already given. Mole fraction already calculated, same mole fraction, this mole fraction. And after that these things, partial pressure, this for the pure component they have given the pressure. Then simply you multiply both, okay, in the place of Y1 mole fraction, and after that given pressure, vapor pressure 200 or 415, that you multiply. And in first case 0.688, that is for dichloromethane, into 415, then you will get you can say 285.5 mmHg. This is the vapor pressure in vapor phase. And similarly for chloroform you will get again 0.312, that is the mole fraction, into 200, then you will get 62.4 mmHg, okay. Then now you have calculated both. Then if you can say now you want to calculate mole fraction in vapor phase. Question was just to calculate mole fraction in vapor phase. Then now you have calculated these things. Vapor pressure of both you have calculated. For chloroform also you have calculated, for dichloromethane also you have calculated. That vapor, this is the you can say vapor pressure you have calculated. You can say in vapor phase what was the individual you can say vapor pressure that you have calculated. Now you have to calculate the mole fraction. Then here how will you calculate the mole fraction? Then mole fraction, that formula already I have written you, that is the P1 is equal to Y1 into can say P total. Then Y1 is equal to how much? P1 divided by total pressure. Then now here P1 you have calculated 285. P1 you have calculated 285. Then just to divide it by total. Then total was 347 already calculated. 285.5 divided by 347. Okay, in the beginning total you have calculated, that total. Then after solving you will get 0.82. 0.82. Then now other easily you can calculate. Okay, other just 1 minus 0.82 will calculate, then you will get 0.18. Okay, 0.18. 1 minus 0.82. Then 0.18 you will get, or by keeping the value also you can get, that is the 62.4. Already you have calculated 62.4 for chloroform. 62.4 divided by total 347.9, you will get 0.18. Same way, either in that way or this way, same result. Okay, and here one more thing you should know. Since CS2Cl2 is a more volatile, you should understand chloroform among chloroform and dichloromethane. Dichloromethane is more volatile component than chloroform. Okay, this things you should know. Then which is you can say which is more volatile, then they will be in more quantity in vapor phase. Their vapor will be more. Because they are more volatile. Okay, this is the very, very important. And now I have just finished one numericals also, long numericals, and I think concept is clear. And two formula here you have used, 2-3 formula. First formula you have used for mole you have calculated. After that mole fraction you have calculated 2. And third things you have calculated, after the mole fraction you have calculated total pressure, total vapor pressure you have calculated. And then this total vapor pressure you have calculated by using the formula P10 plus P20 minus P10 in bracket outside X2. Then P1, P2 value was given in question. Then by using an X2 value also you are knowing, mole fraction you have calculated. Then this total pressure you have calculated. And when total pressure you have calculated, then to solve the second part you have calculated pressure, vapor pressure of each you have calculated by using total fraction and mole fraction. Total vapor pressure and mole fraction, by using these two you have calculated these things, vapor pressure of each in vapor phase. Vapor pressure of each in vapor phase means P dichloromethane and P chloroform you have calculated. And then when this you are knowing, when total you are knowing and P1 you are knowing, then Y you can calculate very easily, P1 divided by total. In both cases you have done like same way. Then here it is very good question, but they will not ask so long question, but part by part they can ask. This concept is useful. Okay, then now I am stopping only here. Next class again I will continue. Thank you.